but I've known Ellie for a while now. He's going to talk to us today about ultra energy cosmic rays from gamma ray bursts, which ties together our first topic, which where people like Tony Bell told us about sources of ultra high energy cosmic rays and gamma ray bursts. And Ellie, I guess, started out, he can correct me, in more applied areas like plasma physics, and decided to become more speculative and join the astrophysics world by showing up at the Institute of Advanced Study in Princeton, where I met him. And then he went back to Israel and took up a position at the Weizmann Institute, and he's been there ever since. And as you've been hearing, he's been very busy, not just on the astrophysics front. On the astrophysics front, besides ultra energy cosmic rays, he's had students that worked on shock acceleration and supernova blast dynamics in general, and radiation processes in blasts. And he's also, some of you may know, he's an expert in neutrinos, and he's the Waxman and the Bacall-Waxman bound on the luminosity of extragalactic neutrino sources. And also, as you've heard, he's advised the government in several capacities, I think, most recently on COVID-19. And for today's topic, going back to the mid-90s, it was sort of a perfect storm for the topic we're going to cover today, because Batsy and Beppo Sachs had proven conclusively that most GRBs are extragalactic and thus very distant and very powerful and relativistic. And as Tony told us, those are good ingredients for cosmic ray acceleration, although Tony might prefer to have the system be a little bit less relativistic. But nonetheless, that makes them prime suspects. And also around that time, we had the evidence for ultra energy cosmic rays was solidifying, and we got better estimates of the fluxes and things like that. So it was a combination of GRBs and ultra energy cosmic rays that I think led Ellie to work on this topic. And so without further ado, let's let Ellie tell us about it, and maybe if there are any updates since when he first started on it.
I will be talking about gamma ray bursts and their possible connection to ultra energy cosmic rays, and also neutrinos. Oops, I lost the cursor for some reason. Okay. The sources and the acceleration mechanisms of cosmic rays are largely unknown over most of the energy range over which these particles are observed. In today's talk, we will focus on the ultra high energy end of the spectrum beyond the 10 to the 10 GeV, where the flux of particles is too low to enable detection, direct detection in space, and particles are detected only through their interaction in the atmosphere. Since the particles are not detected directly, the composition or the identity of the particles is not well constrained at this energy range. And we have evidence that the composition is going from lighter to heavier, but we don't have solid constraints, as I will show. At these high energies, regardless of their identity, the particles are not confined by the galactic magnetic field, and they are most likely originating from extragalactic sources. The exact location of the galactic to extragalactic transition, which is probably close to this 10 to the 10 GeV, is not well known. And the sources and the acceleration processes are not known. What I will try to cover is first why these high energy cosmic rays are interesting, then why gamma ray bursts are likely candidate sources for these particles, what we know and don't know about the properties of the ultra energy cosmic rays, what the experimental status of the testing the GRB cosmic ray association is, and finally what the prospects are for making progress on this in the near future. Let's start then with why the particles are interesting. So they're interesting because it is very challenging to build a theoretical model for the acceleration of particles to the observed ultra high energies. Charged particles are accelerated in astrophysical sources, most commonly by generating an electric potential through the motion of magnetized plasma. So if you imagine a source driving a flow and outflow of magnetized plasma, and imagine encircling the source with a conducting wire, the potential drop across the wire would be given by the time derivative of the magnetic flux, which is the velocity times the magnetic fields times the radius of the object, of the wire. And this sets an upper limit to the maximum energy to which a particle can be accelerated depending on its charge as it goes down this potential drop. Now, if the outflow is relativistic, we are able to utilize only 1 over gamma, 1 over the Lorentz factor of this potential, because as the plasma expands from, say, R to 2R and the magnetic field drops, the time in the rest frame that the particle being accelerated experiences is R divided by the Lorentz factors times C. So it can only travel a fraction of 1 over gamma of the radius, and therefore the maximum energy is smaller by a factor of gamma. Now, this outflow of plasma carries some energy with it, and the lower limit to the energy output from the source is the energy carried by the magnetic field. Using this lower limit or the upper limit on the energy and lower limit on the magnetic field in the estimate of the power output, we get a robust lower limit to the power output from the source, which is 10 to the 12 solar luminosity for a particle with rigidity energy divided by charge of 10 to the 11 GeV. And this is for sort of an optimal accelerator where both the Lorentz factor gamma and the velocity V over C are close to unity. Now, this limit already leaves only a few candidate sources for the acceleration of such particles. And even if you have such a candidate source, it's quite challenging to build an acceleration a mechanism that would fully utilize the potential that is produced. The relation to gamma burst is obvious from this relation. So if the charge of the cosmic ray particles is larger than 10, then the luminosity limit is lower, and there are a handful of candidate sources. However, if protons are accelerated to ultra high energies, Z is 1, then the luminosity limit is such that we have only 2 candidate sources. One is gamma ray bursts and the other is tidal disruption events. Both are related to relativistic jets driven by rapid mass accretion onto black holes. And I will discuss these, especially the gamma ray burst case, in a bit more detail later. Before going to the proton acceleration in gamma ray bursts, let's discuss a little bit what we know and what we don't know about the ultra energy cosmic rays. The most robust data that we have are the flux and spectrum, or the observed flux and spectrum of the cosmic rays. The observed flux and spectrum is determined by the spectrum at which particles are generated at the source and the effective lifetime of the particles since they lose energy propagating through the intergalactic medium by interacting with the radiation fields. So by measuring the flux in the spectrum, we get a combined constraint on the energy production rate, the spectrum, and the composition at the source, but we cannot separate this. There's some degeneracy between the spectrum and the composition and the energy generation rate. Another handle on the properties is the composition measurements at Earth, and this provides a somewhat more direct constraint on the composition, which we will also discuss. And finally, we have some information in the angular distribution over the sky of the cosmic ray intensity. I will not discuss this because we have no strong limits based on this measurement. The flux is roughly isotropic, and we can discuss it in the discussion if you want, but we don't have any strong input from those constraints. Let us start then with the flux and the spectrum. So, if the particles are protons, then their effective lifetime or propagation distance is strongly suppressed above 5 times 10 to the 19 electron volts, where the proton energy exceeds the threshold for producing pions interacting with the microwave background. Okay? So this is this famous Gzk suppression. And if you look at the cosmic ray data, we actually see a strong suppression around that energy. Now, since the flux decreases very rapidly, and if you observe the y-axis here, the flux is multiplied by a large power of the energy, the shape of this decrease strongly depends on the power of energy by which you multiply the spectrum. So it's safer, instead of looking at directly at the observed spectrum, it's safer to look at the observed spectrum divided by the lifetime, assuming that the particles are protons. This provides the generation spectrum, and this is what you see on the bottom plot. You see that the generation spectrum, if the particles are protons, is flat. So equal energy per logarithmic energy beams. So we see a strong suppression, which is consistent with the proton interaction with the CMB photons, and a flat, featureless power spectrum generated at the sources. This flat generation spectrum is consistent with what we see in a wide range of astrophysical objects, and it is usually attributed to Fermi acceleration in non-relativistic or mildly relativistic shocks. So one explanation of the spectrum is sources producing this flat Fermi-type spectrum of protons. Of course, another alternative would be that particles are highly charged, heavy nuclei. In this case, the suppression at 5 times 10^10 electron volts should be put in by hand. It should be attributed to the source spectrum. So that you should assume that the acceleration is enabled to accelerate the charged particles only to the energy that corresponds to the Gzk proton suppression. And the energy production rate above 10^10 electron volts is actually not very different from what you would infer for proton sources. Let us next move to the composition. As we mentioned, the particles are not observed directly, but rather through the showers, the large number of high energy particles that they produce as they propagate through the atmosphere. The main handle on the composition is the so-called Xmax, which is the depth in the atmosphere at which the maximum number of relativistic shower particles is achieved. The average and variance of this depth decrease with increasing nucleus mass, with increasing A. What you see in the top right plot here is the variance of this Xmax as a function of energy from the data of the Auger experiment, which is the largest current cosmic ray experiment. And as you can see, Auger observes a decrease in this variance, corresponding roughly from a change from hydrogen to nitrogen. And when a multi-component fit to the data is attempted, one finds this transition to nitrogen, but with a dominant strong contribution of proton and helium nuclei above 10^10 electron volts because of this high variance of Xmax of those energies. Now, before concluding that this is the reality, we need to be a bit careful because there are very significant uncertainties here. One thing to note is that there are significant discrepancies between different experiments, and not only at the highest energies, where you see here the older high-res results that do not show a decrease in the variance of Xmax with energy. And also at lower energies, if you look at the average value of Xmax as a function of energy, you see a wide spread between different experiments, which is not small compared to the difference between protons and iron. In addition, there are experimental systematic errors and model systematic errors. The blue bar here represents the experimental uncertainty. The red bar represents the uncertainty due to the extrapolation of the interaction cross-sections from the LHC energy to the highest energies at which these particles interact in the atmosphere. So you see that the systematic uncertainties span almost the entire range between nitrogen and hydrogen. And it should also be noted that none of the models actually produces a good fit to the data, suggesting that the systematic uncertainties are even larger. So the composition constraints are at this point inconclusive. Setting aside those uncertainties, one may try to construct a mixed composition model to account for the apparent decrease in this variance of X max. And this is what's shown in this example. Now, models that attempt to do this have several challenges. One, they introduce a maximum cutoff acceleration energy, which should reproduce the Gzk suppression and should be proportional to the charge of the particles. So you need to put this by hand. In order for different species to dominate the different energies, protons, nitrogen, iron, at different energies, you need to choose a very steep generation spectrum so that the energy is all concentrated at the highest energy of the accelerated particles. This is a challenge to acceleration processes. And in order to produce the composition, this variance, you need to choose a composition at the source which is very rich in heavy nuclei, much richer than the normal astrophysical environments that we are used to. And this is another challenge to the models. Now, even after choosing all these ad hoc assumptions, the models still do not reproduce the large variance above 10 to the 19 electron volts. And in order to correct for this, one usually needs to add a significant, like 10% proton component at the highest energies. So if I summarize these constraints, from the flux and spectrum, we know that the sources could either be proton sources with a flat generation spectrum, suppressed by the Gzk interaction with the CMB, or sources of heavy nuclei, highly charged, in which the acceleration is cut off at this 5 times 10 to the 19 electron volts, and where the energy production rate is not very different than the proton production rate. The direct composition constraints are not conclusive at the moment.
Eli, may I question, Eli?
Yes.
I mean, from these two, what you wrote, I would conclude it should be 5 times 10 to 19 per nucleon, or just simply 5 times 10 to 19 acceleration cutoff?
5 times 10 to the, no, 5 times 10 to the 19 cutoff, which means 5 times 10 to the 19 divided by the nucleon number per nucleon. Per nucleon, yes.
Because otherwise, we would conclude that everything above 5 times 10 to 19 are protons.
Yes, no. This is the Z times the energy per, or A times the,
yeah, per nucleon, okay.
Yes. Okay, so the, we cannot draw a robust.
All right, just to correct it, it's per charge particle, per Z.
Yeah, E over Z should be, E should be, E times Z should be 5 times 10 to the 19 electron volts, where E is the energy per charge. So it all depends on the rigidity. E over Z should be fixed. If it's proton, the energy of the proton is 5 times 10 to the 19 electron volt. If it's a charged nucleus, then the energy is Z times smaller.
So this should still allow that there are no protons 10 to 20, or
Yes.
still should be.
Yes.
I mean, so could be situation no protons at all, 10 to 20.
Yes, but as I said, the no proton models do not reproduce the large variance of X max at the highest energies, and you need to put in some additional component there. If you
So
want
Ellie,
to...
that's really misrepresenting it. With one of the hadronic interaction models, you can get a significant improvement to the fit if you add a high energy proton component. With the other one, you need low energy protons. So the main point that we were making when we wrote that is that it remains very uncertain. Also, you really shouldn't be showing 2015 data when it's 2021. The numbers have gotten much better, and the variant and the uncertainties are much smaller.
Well, the systematic uncertainties are no smaller today. And I was talking about systematic uncertainties, not about experimental, not statistical uncertainties. These are not the dominant.
It's also fair to say that even the systematics have gotten smaller because the high energy interaction models have gotten much better due to both. So anyway, I'll shut up, but you just be careful how you're implying much more uncertainty between experiments. If you look at the joint OJ-TA composition working group, they agree that it's consistent. It's only a few people in high res that and TA that want to argue that it's inconsistent. So it's just a more complex situation than you're saying, I think.
Well, so let me show again this plot. I think that regardless of the model that is being used, and here there are different models, you need a significant fraction of light nuclei at the highest energies. Okay, regardless of the model that you use. Well,
in any event, maybe they'll let me give a talk and I'll express.
You give a talk and you'll confront that. So I think that there's no way to explain this large variance without a significant proton component for all the composition, for all the interaction models. As I mentioned, the discrepancy with all the data still exists. And
no, that is if you read the composition working group.
As you said, you'll give another talk, so you will say whatever you want. But this discrepancy still exists. It's not telescope array; it's high res. And
I'm sorry.
I have also something to say. You cannot twist the facts like that. I mean, first of all, this large variance you're talking about is the 2014 data, yeah? So you say, why do you say large variance? You mean the statistical 2 sigma upward fluctuation here, which in the 2020 data is not there anymore. So I don't think you should use this as an argument. Secondly, if you point out this light composition in the Auger fits, you should also see that with the EPOS interaction model, the points, the slide before you show, the points are actually consistent with 0. So also there, you're not making a really strong point here. And as Glenny says, the newest data from Yakutsk telescope array and Auger agree perfectly well in mean X max and sigma X max. Now, to show this plot on the lower left, which is like from 2005, I don't know what you wanna prove with that. So this old data, we don't even know what is the systematics of this old data on the left-hand plot. So I think you should really focus on the experimental situation of current experiments with that have the highest exposures like TA and Auger. And there's no doubt that the variance really drops with energy. Yeah, and then the systematic uncertainty that you were quoting, it's also not correct that it's between nitrogen and hydrogen, right? So hydrogen has a 5 gram uncertainty, yeah, but this uncertainty in the elasticity, if you have a compound nucleus like nitrogen, is not the same for nitrogen. So it's no way that you can change the models that hydrogen looks like nitrogen. You can
excuse me, maybe I just say I ask very short question just to clarify, but if you have log comments, better we just do that after that, because and this
we
is
can have an actual
major,
talk about experimental results too later.
Yeah, there's not a major idea of I just want to simply clarify one question, and if short talks maybe is okay, but comments better we leave after the talk. Sorry.
So do you want to?
I would like that you're hearing.
Again? I didn't hear the last question. Okay, I will. So I think that we can have a longer discussion of this issue later on if you want, of the uncertainties. I would just mention one more comment about using EPOS, which shows less discrepancy. I believe that this EPOS model is actually inconsistent with in other reproduces the Xmax data, the Xmax variance. And okay, I will stop here and continue with the discussion. Let us go to GRBs. GRBs are the brightest known objects. They produce a luminosity of 10 to the 52 ergs per second for a few seconds and show millisecond variability. And in some of them, we see 100 MeV photons, not in all GRBs, but in a significant fraction. Most of the models for explaining these gamma ray bursts involve relativistic jets driven by rapid mass accretion onto a black hole or a neutron star, with Lorentz factors reaching a few hundreds. The lower limit on the Lorentz factor is based on the observation of 100 MeV photons escaping these jets. Broadly speaking, there are two classes of models. One is electron proton dominated jets, where the energy is produced with the kinetic energy, part of the kinetic energy of the jet is converted to thermal energy by internal collisions within this expanding outflow, and electromagnetic jet models where the jet is dominated by, let's say, Poynting flux, and the dissipation is of energy of the jet that is converting energy to high energy particles, and radiation is through some dissipation mechanism of the magnetic fields. I will talk about the electron proton jet models very briefly. So in these models, we have a compact object that drives a highly relativistic outflow, which is highly variable, and the variability of the outflow leads to internal collisions within the expanding outflow on a radial range of a few times 10 to the 12 to a few times 10 to the 14 centimeters. And then as the expanding plasma interacts with the interstellar medium, it is being decelerated, driving a shockwave into the interstellar medium and another shockwave that is driven backward into the ejecta and decelerating it. The gamma rays are believed to be produced in these models by particle electron acceleration in the internal shocks within the expanding outflow, and the acceleration of electrons by the shock driven into the interstellar medium produces the afterglow radiation at lower frequencies on timescales much longer than the emission of the gamma ray bursts. Wherever electrons are accelerated, we also expect protons to be accelerated. And I will discuss both the proton acceleration and the internal shocks and in this reverse shock of the ejecta. In both cases, the internal shocks and the reverse shock that decelerates the ejecta are mildly relativistic in the rest frame of the outflow. And we believe that Fermi acceleration can operate there quite efficiently. And this will enable acceleration of protons up to the 10 to the 21 electron volts, as we have mentioned. Now, the reverse shock is particularly interesting in this context because most of the kinetic energy of the plasma is converted to thermal energy by this reverse shock. And the downstream of the reverse shock is just the interstellar medium, so that protons that are accelerated in this shock would escape into the surrounding medium. We can estimate what proton flux would be produced in this model by considering the gamma ray production rate by gamma ray bursts. So if we consider the redshift 0 energy production rate of gamma rays, there's some uncertainty here, but it is between 10 to the 43 and 10 to the 44 ergs per cubic megapascal per year. And if protons are accelerated with similar efficiency, their energy per logarithmic energy bin would be a bit smaller than the electron energy per logarithmic energy bin, because we expect them to be accelerated over a much wider energy range from TeV all the way to 10 to the 20 electron volts. And so their flux is going to be about 10 to the 42 ergs per cubic megapascal per year. And if you compare this to the flux that would be required to account for the entire cosmic ray spectrum, which is quite similar, we would conclude that if proton and electron acceleration of similar efficiency in the GRBs, then they would produce some 10% of the cosmic ray flux above 10 to the 19 electron volts. And if the efficiency is significantly higher, which is not uncommon in astrophysical objects, then it could produce a more significant fraction of the flux. Now, a direct association of protons and photons is impossible because the protons are charged and they suffer very large time delays as they propagate through the intergalactic medium, 10 to the 5 years or more. So there is no way to directly associate these protons with GRBs or other fast transient sources. A possible signature that could be detected is in neutrinos. The high energy protons or high energy nuclei, if they are present, would interact with radiation to produce neutrinos by the production of charged pions that decay into positrons and neutrinos. In this interaction, the outcoming neutrino carries some 5%, 1/20 of the energy of individual nucleon in the parent nucleus, or 1/20 of the energy of the proton. The flux can be estimated using the energy production rate of the cosmic rays. So if we assume that if the particles are protons, we get an upper limit to the neutrino intensity by assuming that all the proton energy is converted to pions, which decay into neutrinos. And this would give 10 to the -8, roughly GeV per squared centimeter second steradian of neutrino intensity. And this, by the way, would be, okay, I'll comment about this later. Now, this bound is expected to be saturated at two places. If the particle flux is dominated by protons, then the flux would be saturated at around 10 to the 10 GeV, because the protons lose all their energy to pion production in interaction with the CMB. These are the Gzk neutrinos. And if the cosmic ray production is related to star formation activity, we expect most of the cosmic rays be low in energy of about PeV, or rigidity of PeV, over Z of PeV for charged particles, to be converted to pions, because most of the star formation in the universe have occurred in star-forming galaxies, and these galaxies act as calorimeters for such lower energy cosmic rays. And this saturation is going to be similar for protons and for heavy nuclei, because the neutrino energy that will be carried out per nucleon is similar for the two species, and the confinement is the same for particles of the same rigidity. So we can estimate what the neutrino flux that could be expected for GRBs is. We need to estimate what the fraction of the proton energy is that would be converted to neutrinos in these objects. Now, while high energy protons can be accelerated at all radii to dry energies, the efficiency of neutrino production is small at large radii. And a significant production of neutrinos can take place only if internal collisions occur at small radii due to variability of about 10 milliseconds. Okay? If such collisions take place, which would be the case if gamma rays are produced in this type of collisions, then the number of interactions that the proton would undergo would be about 1. This probability of interaction can be directly related to the optical depth for per production of 100 MeV photons. And if indeed the optical depth for these 100 MeV photons is about unity, this is where the lower limit to the Lorentz factor comes from, then each proton above an energy of about 10 to the 7 GeV would interact once and lose about 10% of its energy to the production of pions. And so The internal shocks, if they are responsible for producing the gamma rays and they occur at small enough radii, we would expect a neutrino flux, which is about 10% of the flux that would be observed if all the high energy cosmic ray protons convert their energy to pion production. Okay. What is the current experimental situations? So IceCube Eventowers, which are large Cherenkov detectors for detecting high energy neutrinos above around 100 TeV, have set upper limits on the flux from GRBs, which is about 0.4% at 0.1 PeV, 100 TeV, and weaker limits at higher energies. So this upper limit is comparable to the predicted flux, assuming that GRBs produce a significant fraction of the ultra energy cosmic rays in protons. This limit implies that either this fraction is a bit smaller than unity, or that the optical depth for 100 MeV photons is a bit smaller than unity. So these limits are close to the predictions, but they currently have limited implications to the common GRB models. Stringent test of the model, either a detection or ruling this model out or constraining these parameters significantly, would require significantly larger detectors. We should recall that IceCube has detected an extragalactic neutrino flux, which is comparable to the upper limit on the neutrino flux that I've just explained in the energy range of 50 TeV to a few PeV. This is the discovery paper. See the neutrino intensity as a function of neutrino energy. And this is the extragalactic extension of the neutrino flux. And this is the bound flux level. Okay. Now, the saturation of the bound suggests that whatever the sources are, they are related to the sources of the ultra energy cosmic rays. And it is consistent with the expected saturation below a PeV for sources that reside in this calorimetric environments of star-forming galaxies. So these neutrinos are probably not produced within the accelerator. Okay? They are probably produced in the environment of the accelerator after the cosmic rays have escaped, and they lose their energy over a long time, comparable to their energy loss time in the surrounding galaxy. The neutrino flux that we expect to be associated with the prompt gamma ray production is going to be much smaller for all the candidate sources that we know. We've seen the example of the gamma ray bursts where the prompt neutrino flux is 1 to 10% of the flux that was detected, depending on the energy. And this implies that identifying the sources is challenging, and it will remain challenging in the near future. At the present, there is no significant neutrino association with electromagnetic sources, and it is not really surprising based on this understanding that the neutrino flux produced by within the accelerators themselves is probably a small fraction of the observed neutrino intensity. Still, the temporal association of neutrinos and gamma rays is the most promising way to identify the sources. It would be a direct identification of the location of proton or nuclear acceleration. In order to achieve such a possible association, we need two main things. One, we need a wide field electromagnetic monitoring of the sky with real-time alerts to follow up high-energy neutrino events. And we need a significantly larger detector than we have today in order to be able to detect the significantly lower flux the IceCube has detected. We need approximately 10 times bigger detector or 10 times bigger effective mass at 100 TeV in order to have a reasonable probability to detect such an association. Now, what about accelerating heavy nuclei in gamma ray bursts? So in high luminosity gamma ray bursts, those that are 10 to the 52 ergs per second, the heavy nuclei are usually expected to be disintegrated due to the interaction with the radiation field in the jet. We can produce high energy heavy nuclei in those jets, provided that these heavy nuclei are either entrained in the jet at large radii, or that the jet starts out very cold, and so that these heavy nuclei are not destroyed at the inner radii of the jet. And if those particles are accelerated only at 10 to the 15 centimeter radius, so that there are no significant energy dissipation at smaller radii, they could survive and escape. But all these are sort of challenging conditions for these jets. Heavy nuclei are more easily surviving in low luminosity gamma ray bursts, those 10 to the 49 ergs per second GRBs. And because there the radiation energy density is much lower, so that particles could escape disintegration. And these low luminosity GRBs have been suggested as the sources of ultra energy cosmic rays, and also as the sources of IceCube neutrinos. This type of model has two major challenges. One, the total energy output by low luminosity GRBs is about 100 times smaller than the total energy output in the high luminosity GRBs. And so this would require, in order to account for the observed cosmic ray flux, an energy production rate in protons in these objects, which is 100 times or more larger than the energy production rate in electrons. This, of course, cannot be ruled out, and it actually may be the case in certain objects. But this is a major point to remember.
Can I ask a question? Can I ask a question regarding acceleration? I mean, as I understand, you need sufficiently low magnetization to have successful acceleration. I mean, if your magnetization even is 1%, right, then I think this mechanism doesn't work. That's what seems to be implied by simulation. So what exactly do you have in mind?
For those low luminosity GRBs? For the low luminosity GRBs, these are highly charged particles. So they are high Z particles. So they are not accelerating protons to ultra energies, only heavy nuclei.
And I mean, in general, I mean, in all these sources. I mean,
so
these internal shocks should be pretty lowly magnetized. And then, you know, in regular GRBs, you don't actually get an outflow because you have enormous loading. I mean, it's only suppressed when your magnetization is a few percent at least. So my question is, you know, if this is a consideration to. Or you can argue that the internal shocks are not highly relativistic, and then we don't really know. That's another.
So the internal shocks and the reverse shock, as I mentioned, are not highly relativistic. They are mildly relativistic or subrelativistic. Right? Because in the restream of the flow, they are both mildly relativistic and not highly relativistic. This is true both for the internal shocks and for the reverse shock. in
Right. In any case, you have if you have magnetic field, not even 1%, but even 10 to the minus 4 magnetization, regular field will advect particles from the shock faster than it could possibly diffuse upstream. And this general
in relativistic shock, right? No,
even
only in relative.
even mild relativistic shocks. Yeah, this is what we know from simulations now.
Yeah, so it's an issue.
Yeah. I don't think magnetized shocks, but I don't think Fermi acceleration can possibly work in magnetized shocks at all. I mean, mild relativistic or not.
In what?
In magnetized shocks. And by magnetized, I mean transverse field, which is what jets have, transverse field, transfers to the flow direction. And magnetization prime to sigma, 10 to minus 4. 5 could kill it, but yeah, I mean, this is debatable. What's the exact threshold? And depends also on the composition. What we're finding with electron positron plasma, it's not published yet. This is what I'll talk in a couple of weeks about it. But for when you have electron positron mixture to the ions, then this threshold is even lower, 10 to minus 6, even lower. So I mean, if you believe that the jets carry some magnetic field, let's say 10 to the minus 5 of the jet power is carried by magnetic fields, I think regular Fermi acceleration is out. The shocks plasma would be thermal behind the shock.
Right, so in gamma ray burst, in regular gamma ray burst, because they have to, break out of the star, what we find is that if they're purely hydrodynamic, actually the loading is enormous. You get an outflow with a gamma of a few at most. If you have magnetization of, let's say, a few percent at least, then it's suppressed. Then you can actually get a fast outflow above the photosphere. So it's pretty intriguing situation.
Well,
Do we come to that after the talk? Because it's getting a bit long discussion, if it's possible. We'll come again. We have half an hour after the talk. So, but if you have a short question, please. Otherwise,
okay.
Hi. My question is about the low luminosity gamma ray bursts. You addressing them as if they are just regular gamma ray bursts with regular internal shocks and so on, but some people include.
Tzvi, there's a problem with your microphone, or
I believe, wrote papers suggesting that low luminosity gamma ray bursts are shock breakout, and which are different phenomena than low than regular GRBs.
So
I apologize.
So Tzvi, let me repeat your question. I think I understood. So you were mentioning that low luminosity. Tzvi? Okay, let me repeat what Tzvi has said, I think, and answer it. So
I'll reframe the question.
I'll explain it, and if you think if I miss something, you can correct me, because it's difficult to hear you. Tzvi?
We can't hear Tzvi, so maybe you can, if you
Maybe I'll repeat. I think I'll repeat what he said because I think I understand.
Eli, maybe you could do that after during discussion.
Yeah, but it's just since it's written on the slide, then it's a good thing to repeat it.
Okay.
So what? So we can't hear you, and it's. Let me continue for a second, and then okay. So the low lumen.
We fixed your page 26.
Yes. Go ahead.
Okay. So what Tzvi was saying, I believe, is that it is not at all clear that the low luminosity GRBs are produced.
Yes, please go ahead. I have a serious internet problem thanks to HOT.
Okay. So what Tzvi was saying, I believe, is that the low luminosity GRBs are not necessarily produced by the same mechanism of the high luminosity GRBs, and may not be associated with these high Lorentz factor jets, but rather it is more likely that they are produced by shock breakouts, by the emergence of fast shock waves from supernovae with compact progenitors, in which case there would be no ultra energy cosmic ray neutrino production. And I agree. This is the bullet that is shown here on the slide. Okay. So I think that probably low luminosity GRBs are not the major contributors to the ultra energy cosmic ray flux. This is what you wanted to say, I guess. Okay.
Yes.
Okay.
If you hear me, yes.
Okay. Yes, we hear you. Okay. So if we summarize, I think we are out of time more or less. High luminosity GRB jets with 10 to the 52 ergs per second are capable of accelerating protons to 10 to the 20 electron volts. We expect, if they do so, to observe a flat proton spectrum with a proton intensity that is 10% or more of the ultra energy cosmic flux above 10 to the 19 electron volts. If the dissipation of energy occurs efficiently at relatively small radii, we would expect also a neutrino intensity that accompanies the proton acceleration, which is between 1 and 10% of the flux that is observed by IceCube at different energies. The current experimental constraints indicate a heavy composition at energies above 10 to the 19 electron volts, with a significant fraction of protons, which is both allowed and I would also argue preferred for acceptable interaction models. And we have large uncertainties because of discrepancies between models and experiments. So this question is still open. High energy neutrinos, as we said, IceCube detected the flux, which is comparable to the upper limit on the neutrino intensity from ultra energy cosmic ray sources. It is probably produced by interaction of the cosmic rays, not at the sources, but rather at their surrounding galaxies. And what would be required to produce a conclusive test of the association of gamma bursts and high energy cosmic rays would be first a reliable measurement of the proton fraction at ultra high energy, and second, prompt association of neutrinos and gamma rays. These challenges may be addressed in the coming 5 to 10 years by cosmic ray, neutrino, and gamma ray telescopes, which are either operating or under construction. For the ultra energy cosmic ray proton fraction, we may get better constraints from the Auger prime experiment, where one would get a better separation of electron and muons in the shower, and also by the telescope array. For the neutrinos, testing the fraction of cosmic ray protons at ultra high energies through detecting the Gzk neutrinos would become possible if sensitivity, which is about 10% of the neutrino bound, is achieved. And this could be achievable by radio Cherenkov detectors, which are currently being pursued both in the South Pole and in Greenland. And an association of neutrinos with prompt gamma ray emission in gamma ray bursts, but also in other sources, could be achieved if we have a neutrino detector with an effective mass which is about 10 times the current effective mass of ice cube, which is about 1 gigaton, at the energy range of PeV to 1,000 PeV. And finally, in order to achieve an association, we need a wide field electromagnetic monitoring in X-rays or gamma rays in order to associate the neutrino arrival with a photon arrival. So there are, I believe, good prospects for much better constraints on the models in the coming 5 to 10 years. Okay, and I'll stop here.
Okay, we start the discussion session. We could go up to half an hour. So that I think is a good opportunity to ask all questions. I suggest we do a bit in a structured way. So this talk covered 3 different aspects of the problem. One, ultra energy cosmic rays. The second, GRBs, and next neutrinos. Maybe we just start with the cosmic rays, ultra energy cosmic rays. They are just debate about how interpret the experimental data. Maybe we should not go too much details because we already discussed, and that is not the main the topic of this talk. May I just ask one very simple question? As that was want to ask. So the troublemakers for any model for cosmic rays are protons, 10 to 20 protons. I mean, if you go to nuclei, we could relax. On the other, so I mean, the one way we assume that they are just heavy composition, but still we allow to have protons. So it then does matter 10 times less protons or not, problem is still there if there are protons 10 to 20. So my question is the principal question. Are we sure at this moment that we do have protons 10 to 20 eV or more in cosmic rays? Just independent, what is the fraction? Just fact.
I would say no. Yes, we are not sure, I would say. We believe that there are these difficulties in accounting for the data, which suggests that we need some light component there, but I would say that this is still an open question. And
so then it'll be easier to assume no protons at all and because even if we reduce factor of 3, even I mean the 3 times 10 to 19, then it helps a lot. I mean, from the point of view, just any point.
Yeah,
okay,
I agree. If you reduce, if these are dominated by heavy nuclei, then there are wider options for the sources. Yeah. And it reduces the challenge. Yes.
Yeah, but Eli, what I want to say, dominated still is not sufficient.
No, you need to
eliminate.
You need to have negligible. You need to have negligible, yes, amount of protons there. Yes, indeed.
Even negligible doesn't help. Still, we should explain them. So I think either we should have them or not. That was my question. So.
Yeah. Right, I agree, but I mean, experimentally, you would never prove that they are not there. You just prove that they are negligible. And once you prove, if you prove that they are negligible, or that you have no evidence for that you can limit the fraction to some very low limit, then I think this challenge would be removed.
Yeah, I agree. So, Glenis, do you want to comment?
I just wanted to comment on that. I started off, as my colleagues in O'Shea will know, not everybody knows me, I'm mostly a theorist, but in any case, I started off really wanting there to be all or substantial fraction of protons because it would be so much better for theorists. It would make things like GRBs viable. It would make detecting the sources easier. So emotionally, it would be great. And so I spent the longest time trying to find loopholes in the case that there has to be a predominantly mixed or heavy composition, but with a small proton fraction, like 10% or less. And I'm convinced, with colleagues, we even modified high energy interaction models dramatically, allowing for a phase transition in QCD at high energies and things like that. And even those, they could solve superficially the problem, but then we could show that other data about correlations between Xmax and the ground signal would rule those options out. So honestly, it's just not realistic that there can be more than 10% at the highest energy. I personally believe that it's likely there's many different kinds of sources, and I'm rooting for GRBs to be part of it. But I agree with you, Felix, that solving 10% of the problem is not the main goal right now. It's solving 90%.
Yeah. So it seems that we are in agreement. As Felix said, and as is written on the slide, the real issue is to have a reliable measurement of the proton fraction. If they are 10%, as Felix said, the challenge is there. We need the sources that would accelerate those protons to the 10 to the 20 electron volts.
But we don't.
And it doesn't. The issue is not whether they are producing all the flux or 10% of the flux. Exactly. The issue is that you need accelerators to reach those energies, and this is extremely challenging.
But in any event, it's a little bit like politics, you know? You can get yourself totally preoccupied on the hypothesis that maybe 10% is possible, but it's absolutely not needed, right? It's not excluded, but it's certainly not needed at this point.
Well, maybe I've missed some things, but I haven't seen an analysis reproducing all the data consistently, as far as I know, and certainly not consistent with the post-LHC QGS jet. So, but maybe you will show this in your talk and show that the distribution matches. I don't know, but as far as I know, this is still not the case.
It's like saying until intervectin is proven not to work, we have to assume that it might work.
No,
I mean, it's in that category, Ellie.
I didn't understand. Do you get a good fit to all the data?
No, I'm saying that right now it's fair to say that high energy interaction models are not able to fit all the data if you ask accelerator data and cosmic ray data. So there's definitely an uncertainty. On the other hand, there's been huge progress in lots of aspects that you maybe aren't following about internal consistencies of the event generators and so on. And so there are, one model will have a problem with one aspect, and another model has a problem with another aspect. But the nature of the problem is getting more and more clarified by data. For example, new data from Auger shows that the fluctuations predicted by the model are accurate. And so what that implies is that the highest energy interactions in the model are not the source of the problem. It's very possibly a lot of accumulated low energy sort of boring, not really boring to particle theorists, but relatively unsexy parts of the modeling that are likely implied. But anyway, there is progress getting made, but it's certainly, at this point, I do not think anybody could produce a model with anything more than 10% protons. And the reason it allows as many as 10% protons is essentially statistics, that there's not sufficient statistics to allow a subdominant possibility.
Glenis, could you put in different way? I mean, not statistics, just you take only the events with energy more than 10 to 20 eV. Or, I mean, I don't know how many you have, 10, 20, whatever, right? And then, well, in principle, there are methods just to, with high confidence, claim that this could be proton, like we do with gamma rays and the protons. Like, for example, the adding Cherenkov light. I don't know. There is a principal way to exclude nuclei. Just keep only protons.
That's a nice suggestion, Felix, and I think we could dedicate an analysis to that. But let me understand clearly: is the goal to say that none of the events above 10 to the 20 are protons, or that not all of them can be? Which is the goal?
If you can find one confidently saying this is a proton 10 to 20, that will be already a great thing, because like Landau-Pomeranchuk effect, I don't know. There should be some new effects at these energies.
Well, certainly with my various postdocs and students, we've pushed so hard to find some sort of change, but we were more, in the models of the high, like there was a wonderful model where a light ultra boson could create a kind of index of refraction in the atmosphere and whatnot. But we could always in the end exclude it by looking at correlations in the data, especially if powerful correlations between what Xmax is and what the ground signal is. But in any event, I think I like your suggestion to just look individually at the very highest energy events and examine them and say, of these events, what things can we say with confidence about them? I think it's a lovely suggestion.
I can tell you just one example, maybe irrelevant, that, the Lhasa now, he detects gamma rays, background free. And then so it was a bit unexpected. Okay, maybe for me, but not for others. But now suddenly we are there, Lhasa operates in the regime with individually, you say, this is a gamma ray, this is the protons. So maybe something could happen at these energies, who knows? Because I, for example, was very pessimistic about such a rejection power for Lhasa. And then, but it appeared, it works. And because there are a lot of muon detectors, so these fluctuations, you could feel that level of or less.
And there's, I'm sure you know, Felix, but maybe others don't, that there's this major upgrade of Auger, which is nearly done, adding a muon electromagnetic separators to the ground array and adding radio telescopes for measuring showers even during the day and at large angles. And that's going to give a huge advance in the ability to individually discuss the composition of individual cosmic rays. So,
just quickly, would rejection of helium be as efficient as for protons at 10 to 20? Like, is helium rejected? Helium.
Is that a question to me?
Let's say, yeah, to everyone, but to you guys, let's say, yeah.
Helium is much more nucleus-like than a proton is nucleus-like. I haven't specifically looked at that particular distinction, but rejecting helium will be much harder than rejecting protons. Okay. Oh, one thing I might comment apropos of the proton question is in a work with my student Chen Ding and Noemi Globus, which was published in APJ Letters last January, we looked at the anisotropy distribution of the ultra-high-energy cosmic rays. And what we found was an excellent assessment, a prediction for where the anisotropy would be concentrated and what its magnitude would be, even up to around 40 eV. And the underlying model was that it's a mixed composition model, and that the source is, we use the matter density that's been now mapped out pretty well of the local universe as the sources. And then beyond that, we just use a continuum. But in any event, we could show definitively it couldn't be 100% protons, because if it were 100% protons, we would see a strong concentration in the direction of the Virgo cluster, which is not there in the data. we didn't try to put an upper limit on the proton contribution, but which would be in a next generation phase. But interestingly, I do think it encourages the idea of transient sources, because in order to have it follow grossly speaking, follow the large scale structure and not the closest local event, it's kind of natural then for the sources to be more sources that are individually fairly weak. Anyway,
so
could we move to GRB part of
let me just ask, I still want to understand Glenys, but I'm not sure I understood her answer. So where is the analysis that shows that you can explain the distributions with existing interaction models and without a light composition?
Without what?
Without any light contribution of protons or helium.
The paper is Ding, D-I-N-G, Chen Ding, Noemi Globus, and me.
No.
And it was Apj letters this year.
No, this is a different thing. I'm asking whether there is an analysis that shows, that removes this discrepancy of the high variance in X max with existing models.
I'll try to say, I was just in the process of trying to find paste into the chat. It's a paper with my student, Marco Muzio and Michael Unger, where it's a refinement of this model, and it's
I believe that this is the 2019 paper, right?
Oh, no, 2021. It's on the archive. I'll send the reference in the chat. I've been having internet connections problems, but I just think I got it organized, so I'll put it into the chat.
And you say that you reproduce the variance also with only heavy composition?
Yes. It's just it's fair to say there's a couple of data points where the error bar on the variance is big, but a comment I want to make is that the variance has this issue until you get a lot of events in a particular bin, so you can measure the variance well. Measuring a variance is always subject to changing dramatically.
Glenys, I guess,
one more event.
I guess, yes, the whole issue is this. Just these few points.
You've got to quit looking at 2015 data, Ellie. The picture is totally improved. So I'll share the screen and I'll show you the present data and the present fit. So you continue on the theory and I'll find the.
Let's move to GRB part of questions. And then we already had some questions regarding the acceleration efficiency in highly magnetized flows. So we could continue. I see also the question by Evgeny Derishev. Before, just another related question. I understand all these difficulties of accelerated particles in highly magnetized flows. I mean, that one thing. Another is, what is the absolute value of the magnetic field in the zones when you have 10 to 20 eV particles? Just approximate scales. I mean,
so could you repeat that? You were sort of.
What is the typical value, typical strength of the magnetic field in the zone when these 10 to 20 particles are accelerated, supposed to be accelerated?
So this depends on the radius that you assume. So this B times R is roughly independent of the radius. So if the dissipation is at very small radii, it would be a Gauss in the rest frame of the object, of the plasma. And if you move to much larger radii, like 10 to the 15 centimeter already, it's a milligauss in the rest frame of the plasma.
Yeah, okay, that is safe side. Because of synchrotron losses, you could not accelerate more than 10 to 19 if it's more Gauss. I mean, so it's less.
Yeah, so
okay,
one of the
yep.
Yeah, so one of the interesting points which I did not mention is that in order to avoid the synchrotron losses, you obtain a lower limit to the Lorentz factor, which depends on the radius or the variability time. And for the lower range of the variability times of tens of milliseconds, the lower limit on the Lorentz factor is about 100 from this consideration, which is independent of the constraint from the 100 MeV photon escape.
Okay, then maybe, I don't know, I interrupted Andre and Ami during the talk, so maybe you could continue also, but before maybe Evgeny Dereshev has a question.
I want to ask, you said that the particles should be accelerated, that protons should be accelerated at internal shocks, and there, due to high density, they produce neutrinos, and this is the signal you want to look for. Now, there is a common notion that in GRBs, internal shocks are most likely radiation dominated. Do you think it's consistent with acceleration of protons or not?
So I believe that, we need to separate these two questions. First, acceleration of the charged particles would occur at all radii, from the very smallest interaction radii to the interaction with the interstellar medium, and reaching the same energy roughly. And the more likely region where particles will be accelerated and be able to escape to the interstellar medium is the larger radii. For the production of the high energy particles themselves, the larger radii are probably the location. Now, if you want to produce neutrinos, you need to have interaction. You need to have collisions at smaller radii, and there, if the shocks are radiation dominated, then you would not get a significant fraction of protons accelerated, and therefore also not neutrinos. So this does depend on the.
So, do you think there is a way to avoid radiation-dominated shocks, or what's the way out?
Yes, I think that. Well, so in order to get radiation-dominated shocks, you need smaller radii and smaller Lorentz factors. So it really depends on the model that you assume. If you go to if you assume that all the generation of gamma rays is through dissipation at high optical depth, which you need for these radiation-dominated shocks, then you would not produce neutrinos there.
Okay, thank you.
So I see there are no more.
Let me ask a question. Phoenix.
Yeah, go ahead, Amir.
Ali, actually, you mentioned something very interesting about this gamma ray and the neutrino coincidence. This is from a gamma ray burst, right?
Yes.
So, what do you think that what's the difference, the energy between the neutrino and the gamma ray, and what is the flux difference between these two?
The energy difference and the
difference between the gamma ray and the neutrinos, the typical energy from the,
So the typical energy of the neutrinos would be about PeV. This is
PeV.
where PeV, yes, 1,000 TeV. This is
so what is the energy of neutrinos then? The gamma rays then?
The same.
So no, the gamma rays are at MeV. So if this interaction takes place, it's between the MeV photons and the roughly 10 to the 7 GeV protons. These two would be in the rest frame of the plasma, corresponding to the pion production threshold. So these two, from the energy of the photons and from the Lorentz factor, you get an estimate of the neutrino energy, which is about a PeV.
Eli,
Okay.
in this regard, I mean, you indicated also 0.1 PeV, but these neutrinos are a bit irrelevant to, of course, they are produced in interactions 10 to 20, but first of all, their peak is, as you said, is 1 eV, 10 to 18, 10 to 19, and then it drops. So, but even let's assume somehow also they are produced also many PV neutrinos, but always I would argue that, well, who cares? I mean, this coming claim that they are coming from 10 to 20, maybe they are accelerated 10 to 16 producing 1 PV. So probably these PV neutrinos or ice cube neutrinos will be less confident to claim 10 to 20 acceleration if we detect them. So I certainly think we need 10 to 18, 10 to 19 for a robust conclusion.
I would agree. I would agree with you. So these neutrinos would only show that you accelerate to 10 to the 17 or 18. Detecting much higher energy neutrinos is going to be much more difficult because the flux is dropping, and the cross section for interaction is not increasing rapidly. So
yes, I know that, but in principle, if I say this is a strict signature of 10 to 20, then we need highest energy neutrinos 10 to 18, 10 to 19. Otherwise, debate, I could say, okay, these are accelerated up to 10 to 15, 10 to 16. So it's a Pevatron type accelerator GRB, and then you see these neutrinos. Maybe they are coming from highs, but we cannot be sure in that.
We will not, I agree, we will not be sure in that. What it would tell us is that these protons are accelerated to high energies in those environments. So if there were now questions about whether if the shocks are radiation dominated, and then you do not get acceleration of particles, okay, it would resolve this question. Or the question that Amir and Andre were raising about the efficiency of acceleration. Okay, so these issues would be sort of resolved. It would still not be a proof that you get all the way to the highest energies, I agree.
Yeah. So can I follow up on this? So it seems, I mean, if we forget about the wishful thinking that we can detect neutrinos as a signal, it seems like favorable conditions for acceleration are during the early afterglow phase, no? I mean, because there you have a strong shock which is unmagnetized more or less. So, you know, you may not detect neutrinos, but that could be the source of.
No, for the cosmic rays, I've tried to say this a few times. So the cosmic rays, you can get acceleration at all the radii from the innermost up to the reverse shock into the interstellar medium, and maybe even also after, but this is questionable, if you can accelerate particles to dry energies also in the forward shock. The neutrinos come only from the inner regions. So you may not get neutrinos, but still accelerate the high energy particles. This could well be the case.
So then the question, how can we identify the sources in that case?
So
there's no way.
I would say, well, that there are some important things. I think if we measure the neutrino intensity at 10 to the 19 electron volts, and this is measurable if the proton flux is not completely negligible. This is doable. And this would be a very clear indication of the presence of protons at ultra high energies. And so this is a real possibility. It could be done with the radio Cherenkov detectors. So this would be a very strong constraint on the accelerators. And as Felix said, even if it's 10% of the flux, it rules out almost all the accelerators. And otherwise, if we don't detect a prompt association, I think it would be impossible to identify the sources. There's no way, because the cosmic rays themselves, they arrive late, smeared, delayed, deflected, and so on. So the only chance is this prompt association with neutrinos.
Could I just chime in on this just quickly? It's just that, I mean, it follows on from what we've had at previous meetings where this question about the magnetization for the forward shock at least comes up, because it's an important parameter for saying, dictating how large the inverse Compton component of a GRB in the afterglow phase would be. So there's a natural connection between this magnetization parameter, modeling of GRB afterglow emission, and then also a statement connected to that on how good a GRB would even be as an ultra-high cosmic ray source in the afterglow phase. Because if the magnetization is very low, we're not going to get to these ultra-high energies. So maybe in a slightly more indirect way, we get information that brings something to the table.
So I think that in principle, in the forward, if magnetic fields could be efficiently built in the forward shock, which is highly relativistic, which I think this is an issue, which is I think it's open. Then you could accelerate particles all the way to the highest energy, also in the early afterglow phase, not after it slows down dramatically, but in principle you could do that. But I think this is an open question on whether you can amplify the fields there sufficiently.